Welcome back to Groups Involving Sets, and we are still talking about part 1 of Groups Involving Sets. And today we should continue what we did in the previous video, so please, if you didn't watch the previous video, go ahead and watch it. And today we will talk about some extra exercises in this regard. And today we will continue with example number 3, which we want to prove that b minus a, or the difference between b and a, is equal to b if and only if they have an empty intersection. So again, we have if and only if. So this question is actually two questions. The first one is b implies q, which means if b minus a equal to b, then we need to prove that their intersection is empty. And then we have to go ahead and do the second part, or the second direction, which is q implies b, which says that if the intersection is empty, then b equals a equal to b. Okay, so that's what we are going to do. And for this question, and usually, let's do part number 1 now, and let's see how we're gonna prove such a statement. But I would like you to pause the video for a second, think about the question yourself, have a strategy, think of what we can do, and then play the video again and see if we get the same idea or not. So please pause the video now and check. All right, we are back now. Usually, and this is kind of a hint that we usually do if we want to prove that something is empty. Usually, if we want to prove something is empty, we do it by contradiction. So we would assume and we would suppose not. That's it. Assume that the intersection isn't empty. Of course, in addition to the fact that b minus a is equal to a. And hopefully, after many steps, we want to reach to a contradiction. So that's what we are trying to reach. Now, why did I assume that A intersection B is not empty? Because if something is not empty, for sure, we will get an X inside that set. So there exists an X in the intersection. And from here, we want to at least try to do the steps. So X is in A and X is in B. Let me do it in a different color here. And X is in B. This is the meaning of something in the intersection. However, I know what is B. I know it. It is equal to B minus A. So all I will do is I will write the same statement again. But here I will just change X, B into B except A. The reason why is B minus A is equal to, just to remind you of how things are going. Now, something in the difference between two sets, it has a meaning. Let me write the meaning and see where we are going with it. So X in A and X is in B and X not in A. Now I see the contradiction. Look at the first statement and the last statement. Do they contract each other? Are they the opposite of each other? Can both of them happen at the same time? Look at this and look at this. Focus on them. Of course not. This is X in A, this is X not in A. They are contradicting each other. So we reach where we want to reach and we got a contradiction. And this is the proof of contradiction and this is the power of the contradiction. Why it's a contradiction? Because I'm saying that X is in A and X is not in A. I will just put a line so that you remember where and from where we get the contradiction. And once we get the contradiction, exactly, it will help me to visualize my proof. So please look at the proof. Let me go through it quickly. We said we will prove something equal to empty by using the contradiction, because the contradiction will give me an idea that this is not an empty. So I will find an X inside something which is not empty. And then because X is in A, X is in B, and B is equal B minus A, if I just analyze this one, I get both of them. And finally, I will get where I need to reach. Now, let me go to part number 2. And here, I have to assume that they have non-empty intersection. And I need to prove that B negative A is equal exactly to B. Of course, this question I can solve it with direct proof by contrapositive, because remember I can do it by contrapositive or by contradiction. So whatever you like, whatever you prefer, we can do it in any possible way. So let's do it with maybe direct proof. So I will assume X is in A intersection B, and the required for me is to show B negative A equal to B. Of course, this means we have to show two things. The first one is B minus A is subset of B. And this is, of course, done because B minus A, it means I'm taking something out of B. So it is automatically subset of B. I don't need to prove it. What actually I need to prove is B subset of B minus A. That's what we need to prove. So just let me zoom in, prove this. That's all what we need to prove. Before we continue further, I would ask you to pause the video now and try to prove that B is subset of B minus A. Can you prove it or not? That's what we want you to prove next. Okay, now how do we prove that something is subset of another thing? Remember, we have so many things that we can prove, so many methods to prove, and we can use the, I don't know which method we can use. We can use the, oh, sorry, I think I missed it here. This should be A intersection B is equal to the empty set. Okay, now, how do we prove that B is subset of another set? I will use the contradiction. So I will assume X is in B and X is not B. Now, if you think about it, I'm saying that X is in B, but X is not in the difference between B and A. This means X is in B and X is in A. Why? Because I'm saying that X is not in the difference between B and A. It is not purely in B. That's what this means. Remember that the set difference, this is B, this is A, this is the set difference. This is B minus A. Now I'm saying that X is not in the shaded place, so definitely it should be part of A. And of course it is part also of B, so X is part of the intersection. And this is a contradiction. Why a contradiction? Because the intersection is empty. And that's what gives me the end of my proof. And this is how we do example number 3. I wish you have enjoyed this video. Please like and subscribe.